All right, welcome to Chapter 8. Exciting chapter. It's personally probably my favorite chapter. Throughout this chapter, we cover sort of two thematic ideas. The first one that we're going to look at throughout sections 8.1 through 8.3 is going to be things like sequences and series. So it's really great with stuff like pattern recognition. Um, and that's why I really like it. I think it's something that we're all sort of able to do. It's something that we grew up doing, is looking at like a pattern and figuring out what comes next. The second half of this is going to be probability, which is also sort of nice because you have that sort of real life um, relation to a lot of those questions where you have some background knowledge on it. So it's an interesting chapter. Not too tough either. So first, we do need to talk about a little bit of definitions. So first, we have an infinite sequence. And when we're talking about an infinite sequence, we're talking about a sequence whose function domain is the set of positive integers. So infinite sequences, they're things that are written as a sub 1. So it's a and then the subscript of 1. That's telling us the first term in the sequence that we just call a, comma, a sub 2, a sub 3. And because this is an infinite sequence, this will continue on and on forever until we get to a sub n. And then it will continue on and on after that. A sub n just representing the fact that it could stop, and that changes the type of sequence. So these are the terms of a sequence. The whole thing is the sequence. If the domain of a function consists of only the first n positive integers, so if we stop this at some point and say, okay, we're only going to look at the first 90 terms or the first 1 billion terms, then the sequence is a finite sequence. So we all know infinite versus finite, but just keep in mind that this is how we sort of write our sequences. It's just first term, comma, second term, comma, third term, and so on and so forth. All right, we are going to do some examples throughout these notes. What we're going to cover today is just those first 6 slides, and then there is going to be a second video for you guys that covers the next 6 slides, which is where we get more into the series. Sequences first, then series. So if we have the sequence defined by a sub n being equal to 2 times n plus 3, then when I get all of these a sub 1s, a sub 2s, a sub 3, and a sub 4, what those are telling me is the n values to substitute in to get the sequence. So here I'd have 2 times 1 plus 3, 2 times 2 plus 3, 2 times 3 plus 3, and 2 times 4 plus 3. So we're going to get 5, 7, 9, and 11. So our sequence is quite simply 5, 7, 9, 11. It does technically continue on after that, but we're only looking at these first 4 terms. Right, okay, easy. Everybody knows how to do that. All right, so if we try another one, now we have something that's more exponential or geometric is what we're going to learn about it later. So we have 2 to the first minus 3, 2 to the second minus 3, 2 to the third minus 3, and 2 to the fourth minus 3. So here we're going to get negative 1, positive 1, positive 5, and positive 13. So we'll have negative 1, 1, 5, 13. Now, something to notice here, I'm going back a slide. Here, looking at just these sequence numbers, you had 5, 7, 9, 11, you can realize right away that it's going up by the same amount. That's going to help us later on in writing these sequences to recognize, oh, this is going up by a constant number. In this next sequence, you realize that it doesn't go up by a constant number. It goes up by 2, 4, and then 8. But if you think about those numbers, 2, 4, and 8, those numbers have a relationship to each other as well. It is that 2 is 2 to the first, 4 is 2 to the second, 8 is 2 to the third. So you can see it sort of relates to what's going on right here, or it does relate to what's going on right here. So this is a little bit tougher of a sequence to recognize, but compared to some of the other ones that we're going to do, this is just a cakewalk. All right, what I'd recommend right now is that you guys pause this video. I am going to go on and do this example, but I'd recommend that you pause it just so that you could try it out on your own before I start going over it. So pause right now and then play once you're done. I'm going to start going though. So if you didn't pause, you can just continue listening to me, you know. Now, you're going to see I'm going to write out this first one. -1 to the first power is going to give me -1. 2 times 1 minus 1 gives me 1. And -1 over 1 is -1. That's going to give us our first term. Now, you don't have to go and actually show me the substitution with all of these, because certain things you'll be able to realize. Like in this next one now, I'm going to have -1 to the second power over 2 times 2 minus 1. Now, -1 to the second, that just gives me a +1 over 2 times 2 minus 1 gives me 3. So this is 1/3. Now, with those numerators, keep in mind that if I do -1 and then I just keep increasing the power of it, I'm going to have something like -1 to the first, which is negative, -1 to the second, which is positive. All that's doing is changing the sign. So here I know I'm going to have -1 over something, +1 over something, and -1 over something. And then also looking at the denominator. Again, you can continue writing these out, but think about the fact that we're doing very, very simple arithmetic. We're just doing here 2 times now 3 minus 1. So that's going to give me 5. And you could start to recognize the pattern. So it goes 1, 3, 5, 7, 9. So we're going to have -1/5, 1/7, and -1/9. Don't get too far ahead of yourself on recognizing patterns. Usually you want about 3 terms before you start to use that pattern to continue throughout the sequence. Only because if you have something, if you have something that is something like 2 times 2 or 2 plus 2, you could be getting the same values and not recognizing why. All right, factorial notation. So factorial notation, sort of cool, very, very simple. We define it as if n is a positive integer, n factorial is defined by doing 1 times 2 times 3 times 4 times so on and so forth. This is just so on and so forth, times n minus 1 times n. So what we're really saying there is if you have some number factorial, you just multiply all the numbers before and including that number. Very important, by definition, 0 factorial is equal to 1. That's just how we define 0 factorial. So if we're asking to find 4 factorial, that means that what we're doing is just 4 times 3 times 2 times 1. 4 times 3 times 2 and times 1, which isn't going to change anything, gives us 24. When we do 5 factorial, you can think of that as being 5 times 4 times 3 times 2 times 1. But also just realize that what you're doing here is 5 times 4 factorial, because this is all 4 factorial. When I multiply that, it's going to give me 120. All right, and then we have 10 factorial. Now you're thinking like 10, okay, that's not a very big number. So what we're just doing here is, leisure. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Do you have to usually show that? No, I'll show you how to do it in a calculator. It speeds things up. What you get here, again, 10, not a very big number. You get 3,628,800. So 10 factorial, a small number, gets you 3,628,800, a large number. Throughout this chapter, you're going to see that there are a lot of times in which you are going to get these sort of wildly drastic numbers, and it's not always a thing to panic about. All right, and then we just have a couple more examples. Find an expression for the nth term of the following sequence. So now, unlike the problems where I gave you the sequence formula, So these questions over here, where I gave you the sequence formula and asked for the actual numbers. Now I'm giving you the sequence and asking, how did we get those? What I usually do is sort of think about the fact, and you don't always have to write it, but this is the first term, second term, third term, fourth, fifth, and sixth. And what you're trying to do now is relate these term numbers to the actual values. So 1 mapped to 1, 2 mapped to 3, 3 mapped to 5, 4 to 7, 5 to 9, 6 to 11. And it really is just to find, or about finding patterns. So here I could see I'm going up by 2 each time. Again, we're going to talk later on about what that tells us about the sequence. But I could write this then as saying a sub n is equal to, and what I can realize about all of these is if I multiply the term number by 2 and then take down 1, I get to these values. So it's 2 times n minus 1. 2 times 1 would give me 2, minus 1 is 1. 2 times 2 gives me 4, minus 1 gives me 3. So on and so forth, and it holds true throughout the whole pattern. Again, never ever write something and only check it with like the first term. There's probably an infinite number of ways I can get from 1 to 1. But there's not an infinite number of ways that are going to work through this whole thing. All right, so now I have n equals 1, 2, 3, and 4. Right away, I can realize I went up 2, up 4, up 8. So it's not that I'm adding the same thing over and over and over again. But again, if I think about those numbers 2, 4, 8, they are exponential. They're 2 to some power. So looking at this, if I think about how 1 maps to 2, 2 maps to 4, 3 maps to 8, and 4 maps to 16, I can say that a sub n is equal to, all of these sequence values are 2 to the power of the term number. So 2 to the first gives me 2, 2 to the second gives me 4, 2 to the third gives me 8, and 2 to the fourth gives me 16. So just have 2 to the power of n. I don't know why I made my 2's different. All right, and then last one, we have fractions. The fraction problems are way, way more difficult sometimes. This one, not so much. I will give you a little bit of advice. So with fraction problems, you're looking for really like one of two things. You're looking for something that's going to give you the entire sequence changing all at once, or, and more commonly, you're looking for one pattern for the numerator and then a totally separate pattern for the denominator. So it's not like you're looking for how does 2/3 become 3/5 become 4/7. You're looking more how does 2 become 3, become 4, become 5. And in the denominator, how does 3 become 5, become 7, become 9? The thing that can really throw us off with these fractions is when they are reduced. So, fractions, we sometimes simplify them. It becomes a little bit tougher to figure out what the heck is going on because you have reduced fractions in that mix. You'll see that. It'll be fun. Yeah, you'll hate it. So we have a sub n is equal to, again, this is term 1, 2, 3, 4, 5. Ugh, that's a terrible 5. And what I could realize is all of these are just 1 larger than the term number. So I would say it's n, but plus 1. It's the term number plus 1. And then in the denominator here, you can realize it's almost this pattern right here. So what I did to this 1 was I multiplied it by 2, but then I added 1 instead of subtracting 1. So that's how I'm going from 3, 5, 7, 9, 11. So twice n plus 1. No, I can't cancel off these n plus 1s. They're not the same binomials or anything like that. All right, make sure that you guys go through, mark down any questions that you guys might have that you want to go over, and then make sure that you listen to the second part of the video as well. It will be for a separate day, but it covers the rest of 8.1, which is just going to be sequences.